Hello viewers, welcome back to the course on matrix computation and its application. So, in the previous lecture we have introduced the concept of inner product space. So, in this lecture also we are going to discuss inner product in different vector spaces. So, let us start with the inner product in the space of vector space of polynomials. So, suppose we have a vector space V that is a set of all the polynomials of degree n. So, it is I can say that the set of all polynomials of degree less than equal to n. Now, I know that this is a vector space of dimension n plus 1. Now, from here, now I take a two polynomials, suppose I take p and q that belongs to the polynomial set of polynomials p. This one. So, suppose my p is basically I can call it that a0 a1x a2 x square and an xn. So, this is one of the polynomial that belongs to set of polynomial Pn. I take the another polynomial as b0 b1x b2 x square and bn xn. So, that also belongs to polynomial. Now, we want to find out the inner product of PQ, because I want to say that when I can talk about that P and Q are orthogonal to each other, or I can normalize these polynomials. So, for this one I need to define the inner product in the polynomials. So, the inner product we are defining here is that, because you can see that if we take the polynomial here of nth degree, then its coefficient a0, a1, a2 up to an, that makes a vectors in Rn plus 1. Similarly, I have a q that also the coefficient of this one makes the vector in Rn plus 1. So, I can say from here that a0, a1, a2, an, if I take as a vector, so column vector, so this will belongs to Rn plus 1. So, now we can define the inner product here as summation. So, I can define it as a a0 b0 a1 b1 a2 b2 up to an bn. So, this is same as we are defining here ai's into bi's I from 0 to n. So, this is generally what we are doing, we are taking a simple dot product of the coefficients of the given polynomial. So, this way we are defining this inner product in the space of matrices or space of a polynomial Pn. Now, the thing is that now we are able to define this inner product. So, we need to check or verify all that whether it is satisfying all the 4 condition or not. So, if you see from here, then this is just the dot product, and this dot product we already know that is satisfying all the 4 properties of the inner product. So, this one you can verify yourself that this is a inner product defined on the set of all polynomials. So, now from here I will define the norm on the P. So, this one will be equal to taking the inner product of P itself and then taking the square root. So, from here you can say that this is equal to a naught square plus a1 square up to a n square under the root. So, this is I can define the length of the polynomial or the norm of the polynomial. So, from here if I take, suppose I take a polynomial p and then suppose I take this as maybe 1 minus x plus 2x square plus 3x cube. Suppose I take this one, I take the another polynomial q. So, that I am taking as minus, so I just take minus 1 and then I just take plus 3x. So, and then I take it here, or maybe I just take it 1, then I take minus x square and then I take plus x cube. So, let us take these two matrices or these cubic polynomials. Then I want to check about whether these polynomials are orthogonal to each other. So, I will just take the inner product of this. So, inner product if I am taking, so this is 1 taking the constant and then I will get plus minus 1 into 3 the coefficient of x, then I am taking coefficient of x square, that is 2 into minus 1 and then 3 into 1. So, from here I will get 1 minus 3 minus 2 plus 3. So, this is basically I am getting minus 1. So, that is not equal to 0. So, not orthogonal. But now suppose I take the basis, standard basis. So, let us take, I take the polynomial p as 1 and q as x square. Then I know that if I take the inner product of these two, then this will be 1 and then coefficient of this one 0 and coefficient of x square is 0 here. So, that is equal to 0. So, I can say that the 1 and x square are orthogonal with respect to inner product. So, whatever the inner product we have defined this one, they are orthogonal to each other. So, this is the corresponding inner product. It may happen that we may define the different type of inner product also. So, with this inner product I can say that these two polynomials are orthogonal to each other. Similarly, we can define, now I take the vector space V as set of all the continuous function from a to b in the defined in the closed interval a to b. So, this is a vector space, we know that it is an infinitely dimensional vector space. Then I just take the two elements for this one or two vector from this one. So, let us take f x and g x that belongs to the vector space V. Now, I want to define the inner product this one. So, for this one we take the inner product as from a to b taking the integration of f x g x dx. So, this actually this integration is coming from the dot product, because dot product is defined on the discrete vector, and when we take the function then this dot product change into the integral. So, this is the inner product we are defining on the space of all the continuous function defined over the interval a b. So, now we can verify from here that whether it is a inner product or not. So, we can verify all the 4 condition. Now, the first one is that taking the inner product of f with itself. So, this one you can define as a to b. So, it will be f x into f x. So, it will be f x square dx, and now from here it is a square of the function. So, it is a positive function taking the integral. So, it is value is always greater than equal to 0, and if I say that this integral is 0, that implies that my function f x should be equal to 0, because it is a positive function and positive function, and we know that it is the area under this function f x square. So, area is always positive. So, it is always greater than equal to 0, and if this area is 0, then only I can say that the function itself is 0. So, it is satisfied. The second one is that if I take f and g, then very easily we can say that this is equal to g f. So, it is symmetric also. Third one is that if I take f plus h g, 3 functions I am taking, defining the inner product. So, I can write here f plus h x into g x dx. So, this will be equal to a b. I can write it as f x plus h x and g x dx. So, this one you can say that we can write this as a inner product of f with g plus inner product of h with g. So, this is true for all f h g belongs to the vector space what we have defined here. So, third property is also satisfied, and the fourth property is then I can take any scalar. So, we are defining this one. So, I can take k of f and taking the inner product with g. So, very easily I can write this as k from a to b f x dx. So, I just write first I write like this one k f x g x dx, and I can take the k common. So, then it become the inner product of this. So, this is true for all k belongs to the field. So, here field is a real number. So, all these properties are satisfied. So, based on this one we can say that this is the inner product, and I can say that from here that V the vector space with set of all continuous function is an inner product space. Now, based on this one, suppose I take the vector space, for example, I take a vector space of set of all continuous function defined from maybe 0 to 1, and suppose I take a function f x is equal to x, I take g x is equal to maybe x square I just take. Then I define the inner product of f g. So, this will be taking the integration from 0 to 1, and this is f x g x dx. So, this will be from 0 to 1. So, it is x into x square dx, and then from 0 to 1 it is x cube dx. So, it will be x 4 over 4 from 0 to 1. So, it will be 1 by 4. So, it means their product is 1 by 4 in this case. Now, suppose I want to find its magnitude or its norm. So, this one I can define as norm and I take the under root. So, this will be equal to taking the under root and from 0 to 1 f x square dx. So, this one from 0 to 1 f is my x. So, it will be x square dx. So, it x square dx will be x cube by 3. So, it will be 1 by 3 under the root. So, 1 over under root 3. So, this is the norm of this vector. So, from here I can write the unit vector or normalized vector. Normalized vector we can write as f here divided by its magnitude. So, from here I can write this is equal to x over 1 by under root 3. So, it is under root 3 x. So, it is a normalized vector. I can represent this one by hat. That means its magnitude is 1. So, now from here you can take this one and you can verify that if I take its norm, then it will be 1. So, we have to keep in mind that it is always taking the square root of this. So, this way we are able to find the normalized vector. Now, suppose I take suppose we define another vector space V taking from -1 to 1. Now, in this case I am taking the set of all the continuous function defined from -1 to 1. So, in this case let us I take my function one function f x, I just take x and suppose I take g x is equal to x square. And now, I define the inner product between these two. So, I define the inner product and just to check that whether these two vectors are orthogonal to each other or not. So, I will define the inner product f and g. So, in this case the integration will be from -1 to 1 and f is x and g is x square dx. So, it is from -1 to 1 x cube dx, and you can say from that this is the odd function. So, if I take its integration from -1 to 1, so it is going to be 0. Then I can say that the function f x is equal to x and g x x square are orthogonal. So, you can see from here that the same set of vectors we have taken x and x square on this interval. In that case, if I take the inner product, that was not equal to 0, it was 1 by 4. So, these vectors or this function was not orthogonal with respect to this inner product, that is from 0 to 1. But if I change the interval, then the same vectors becomes orthogonal to each other. So, everything depends upon that how we define the inner product. So, from here we can say that these two vectors are orthogonal to each other under the inner product from integration taking from -1 to 1. So, this is the way we can define. Now, so after dealing all these things in the real vector space, let us see what is going to happen when we deal with complex vector spaces. So, In this lecture, I am going to give you some quick review that how the complex vector spaces are defined. As we already seen that in the complex vector spaces, like suppose I take the vector space V and we call it Cn. So, in this case I am taking the field F. Now, I start with the very first vector space I am taking. So, let us say I take suppose we take the vector space V over C, that is just the complex line defined on the field R, because R is also a field. So, I am defining this one. So, if you see from here, then the vectors are coming from the complex line or complex plane, and this R the scalars are coming from R, the real number. Now, let us see what is going to happen in this case. So, if I know that we know that the vector space V is a vector space, because it satisfies all the condition, and we know that if I take 5 into some vector, maybe I just take 1 I, then it will be equal to 5 into 5 I, and that belongs to the complex plane C. Okay, so, and addition is also well defined. So, everything we can check that this is a vector space. Here I am taking the field as a real number. Now, I want to define. So, we want to define its basis. Now, basis means I want to find a complex number such that we using that complex number I should be able to create all the complex numbers. Now, you can see that, for example, I take a complex number 1 plus I. So, this 1 plus I can generate as, now the scalars are coming for the real number. So, I have to take a k. So, k is coming from real number. So, what should I take the k multiply by vector, so that I get 1 plus I. So, from here I know that I can write this as a 1 into 1 plus I itself only. It means that 1 plus I is created by only 1 plus I, or any complex number a plus I b I can generate only with the help of 1 into a plus I b. It means, if I choose any vector from the complex plane, that can be written in this form, because the scalars are coming from the real line. So, I cannot take those as a complex, it is coming only from the real line, k is belongs to R. So, this is possible only this way, or maybe I can write this as, if somebody says, then maybe I can write this as 2 into a plus I b divided by 2. So, in that case also I can write, but ultimately our concentration is that this can be generated by this way, or I can write any k here, a plus I b by k. So, now from here we found that if I take any complex number, that can be created in these ways. So, from here I cannot say that there is, so which implies that there does not exist a unique complex number, unique vector V, that is a complex number which can span, so which can span the whole complex plane. So, from here we can say that the vector space V with the set of complex numbers defined on the field of real number is infinitely dimension, is infinite dimensional vector space. And complex plane, we you know that A plus I B can be written as, so I take the A on this direction, B on this direction. So, suppose this is my A plus I B, and we also represent by A B, this one. So, it is my A and this is my B, and this is A square B square under the root. Now, suppose I take the vector space V with the same complex. Now, I am taking the field as a complex. So, in this case, for any vector V, that is A plus I B, that it belongs to the vector space V, here we can write A plus I B as taking A plus I B, and the vector I can take 1 here, or I can write as A plus I B by 2 into 2. So, this way also I can write. It means that if I, so this is the same way. So, I just remove this one and I take this here. So, I choose any vector, suppose you take minus I. So, I can write this as a minus I into 1, you just take under root 5 plus 3 I. So, this one I can take as root 5 plus 3 I into 1. So, from here I can say that this whole vector space V is spanned by 1, because all the elements are spanned by 1 by taking all this one. So, here it is the scalar k that is coming from the set of complex numbers, and from here we can say that the vector space V is one dimensional, or I can say V spanned by 2 by this way, divided by 2 into 2, but it will have a basis which contain only one element. So, from here I can say that V is one dimensional vector space. So, everything here we can say that the lot of things changes when we change the field. So, this is where we can define the complex numbers. For example, I just take vector space of real numbers. If I take vector space of real numbers and I am taking the field as set of rational numbers, where Q is set of rational numbers. So, in this case also, suppose I want to find out maybe 5. So, 5 belongs to the vector space V. So, I can write 5 as 5 into 1. So, this 5 is coming from, that is k coming from the set of rational numbers. So, it is rational number and 1. So, no problem. But suppose I want to write a vector, I take maybe root 2. So, root 2 belongs to the real number. So, I can write root 2 as 1 into root 2, because I cannot take here root 2 into 1, because root 2 is not the set of rational numbers. does not belong to the rational numbers. Okay. So, in this case I can write root 2 like this one. So, it means that I am taking a vector that belongs to real line, and this I am taking a k belongs to rationals. I just want to tell that the root 2 is a irrational number. So, it means that all the irrational numbers we have to define in this way. So, this way also I can say that if I take the set of real numbers on the set of rationals, the field, so it is infinite dimensional vector space. And what are the bases? So, I can say that in this case the basis is, I can take all the set of all irrational number, and then I just take union 1, maybe I can take 1, because all irrational numbers are generated in this way, and if the rational number is there we can generate by this way. So, this contains the infinite number of elements, and so it is a infinitely dimensional vector space. But if I take R over R, then we know that this is one dimensional. Vector space. So, till now we have taken such type of things that we are taking the vector space R over R or Rn over R, and in that case we know that this is well defined, but if we change the field then these things may happen. Now, we talk about the complex vector space, just because we want to define the inner product in that one. So, let us define this one. So, let us say take the Cn. So, I am taking the Cn over C. It means that the field I am taking complex number, and this is, so if I take any vector, so let us take u belongs to Cn, it means u is equal to u1, u2, un, and my each ui belongs to the complex number. So, I can write from here that my u will be of this type. I can write like this one, maybe it will be a0 plus I can write this as a0 plus I b0, a1 plus I b1, a2 plus I b2, and so I am talking from here. So, I just start from here itself from the 1. So, it is an plus I bn. So, this is my u basically. So, u is always of this form, because all the components are also complex. So, this will be of this form. So, this is my one of the vector in u. Similarly, I can define the another vector v. So, if you take from here, then I can define my u as, now I can write my u as a1, a2, an plus I times, I can write b1, b2, bn. So, any vector u can be written as, so this is, if you see, that is a real component of the vector u. So, I can write from here that this is equal to a real part of u plus I time, and this is my imaginary part of u. So, I can define any vector from Cn in this way. Now, we can define its basis. So, I know that if I want to define the basis of this one. So, its basis will be again, so I just talk about the standard basis. So, it is n dimensional. So, n dimensional means the basis will be standard will be E1, E2, En, where E1 is 1 0 0 0. So, like this one. So, En is 0 0 0 1, because I am taking the field as a complex number. So, if you take any complex number, I know that I can write u as a1 plus I b1, a2 plus I b2, an plus I bn. I can write this as a1 plus I b1, this is scalar I am taking, multiply by e1, plus a2 I b2 taking the scalar, multiply by this one, and an plus I bn multiply with the vector en. So, these are all are scalars coming from the set of complex number. So, this is, we know that the Cn over the C is n dimensional vector space. So, it is an n dimensional vector space. Now, from here we can, now suppose I just want to see that how we can define the linear combination in the terms of a vector spaces. So, let us take one example. Let us suppose we take C2 and taking over C. So, C is a set of complex number. Some books also write like this one. So, this is also sometime it is written like C this one over C. So, that is also notation, but this is basically set of complex number. Let I take the vector, some vector I take. So, let us take Z1, a vector I am taking from here, and this is suppose 1 and 1 plus I. Z2 I take 1 minus I, and this is my I. So, this is belongs to C2. Now, I want to take, so suppose I choose now for any vector z belongs to C2. Suppose I take z is equal to, maybe I just take it I1. Now, I want to find what will be the coordinates of I1 with respect to the this Z1 Z2. It means I want to find that what are the coordinates of this vector with respect to these two vectors Z1 and Z2. So, what I am going to do is that I am going to define a linear combination. So, in this case I am defining now the scalars will be, if you see from here, the scalar is also complex number. So, from here you just see that I can write here it is a1 plus I b1, this is the first scalar, or maybe I just write it as a1 plus I a2 taking the first vector 1 plus I, then b1 plus I b2, and this is I am taking 1 minus I. So, I have defined the linear combination putting this vector equal to 0. So, you have to keep in mind here that the scalars here, this is my scalar, this is my scalar, that will be belongs to the C, this also belongs to C. So, we have to take it as a complex number. Now, from here I can define this as, so this one I can write component wise. So, from here I can write this is I1 A1 plus I A2. So, this should be equal to A1 plus I A2 plus this one into 1 minus I. So, this is the first one, B1 plus I B2 multiplied by 1 minus I. Next one is A1 plus I A2 multiplied by 1 plus I plus, I am taking this one into I. So, it will be I B1 plus I B2. Now, from here I take the component wise, we can compare this one. So, from here I can say that this will be, so now I can multiply here and collecting the terms. So, maybe I can just simplify. So, it will be A1 plus, I can write from here A1 plus I A2 and then I multiply here. So, it will become B1 and then plus B2, because I B2 is minus I, so it will minus I square B2 and I square is minus 1. So, this one plus I, so I multiply by this, so it will be B2 here minus B1, this one, and similarly I can take from here. So, it will be A1 minus A2 plus I can define here A1 plus A2 plus I B1 plus I B2, and from here if I compare these things, so I can write I1. Now, I take the real part and imaginary part separately. So, it will be A1 plus B1 plus B2, this I have defined, plus I just take it is A2 plus B2 minus B1. Similarly, I can define from here the real and imaginary part. So, it will be A1 minus A2 and I am taking multiply by I here. So, it will be minus B2 plus I. So, it is A1 plus A2 plus B1. So, I get this value. From here, now we need to find out the 4 coefficient A1, A2, B1, B2. So, we need the 4 equation. So, from here I get A1 plus B1 plus B2, that becomes 0. Comparing this one, I will get A2 plus B2 minus B1 is 1, A1 minus A2 minus B2 is 1 and A1 plus A2 plus B1 is 0. So, this is the 4 equation and we need to solve this one to find here. So, if we solve this equation, so we get the value as I got A1 is 1, A2 is 0, B1 I got minus 1 and B2 is 0. So, this is I got. So, from here I can say that I1 is equal to 1 into the first vector. So, it is 1 over 1 plus I minus 1 minus I. So, if you see from here, it is 1 minus 1 cancel out and plus I it will come, and 1 plus I minus I this. So, here we can write the linear combination. So, this is just the simple one we have discussed. So, this way we have to find out the linear combination of the given vector. Now, so if we are able to define the vectors in the complex plane, similarly I can define, if I take C3 over C, then maybe I can define a vector u as 1, maybe 1 plus 2I minus 2I, like this one. So, this belongs to C3. So, same way we have to deal. Now, once we define the vectors, I want to define the matrices. So, this matrices we want to define of, suppose, of order R cross R over complex. It means that the elements of the matrix can be complex numbers. For example, so set of all matrices of order R cross R having complex elements. Complex elements means complex numbers. For example, I take maybe I will define 2 by 2 matrix over the complex number. So, suppose I take my matrix A as 1 plus I, maybe 1, 2 I minus I, one matrix I am defining, another matrix I am defining 1, 0, 0, 1. So, that is also complex number. So, because I know that the real number, each real number can be written as in the form of complex number. So, this is also belongs to this one. Now, suppose I take this matrix. So, I know that this is a dimension 4. So, in this case I know that M 2 cross 2 over the complex number is 4 dimension, and its standard basis and having standard basis as E1 is basically 1 0 0 0, E2 is 0 1 0 0, E3 0 0 1 0, and E4 is. So, this is my standard basis and this is 4 dimension. Now, in this case, now for the complex number I know that we can define the conjugate. So, conjugate of A will be this one, 1 minus I, 1 I minus 2 I. So, this is a conjugate. So, I have to take the conjugate of each of the element in the matrix, given matrix. Now, for the complex matrices, we define the terms A conjugate transpose. We generally write this as A star. So, in this case what we take the conjugate first and then taking the transpose. So, I can write from here that this is equal to 1 minus I 1, it is I and it is minus 2 I. I have taken the conjugate and then I have taken the transpose. So, this is it is called the conjugate transpose. And that is represented by star. Now, for maybe I can for complex matrices or matrices having the complex numbers, if I take A star is equal to A, it means I am defining A conjugate transpose that is equal to A. So, this is called A is an or A is a Hermitian matrix. When I say A star is equal to minus A, then it is called A is called skew Hermitian. So, it is analogous to the symmetric matrix in real number, and this is analogous to the skew symmetric matrix in the real number. So, one thing extra we need to do whenever we are dealing with the set of complex numbers. Then also, if I take any lambda as scalar, so in this case scalar is coming from the complex number, then if I take lambda A any matrix taking the conjugate, then it is equal to lambda conjugate A conjugate. Some observations you can write. Also, if I take the matrix A and taking 2 times conjugate, then it is equal to A. We can write down some properties. Then if I write A conjugate transpose, that is equal to, if I take the transpose and then conjugate, no problem. And the fourth one is, if I take A B conjugate, then it is equal to A conjugate into B conjugate. So, this way we can define the terms in the set of matrices in the complex form. So, once we are able to do this one, then I want to define the inner product in the complex vector space. So, that we are going to discuss in the next lecture. So, we will stop here. So, in the today's lecture we have discussed about the inner product in the space of continuous function defined over a interval a b, and then we want to define the inner product in the case of complex vector spaces. So, we have discussed some properties or how we can deal with the complex vector spaces having the vectors or having the matrices. So, now in the next lecture we will discuss that how we can define the inner product in the complex vector spaces. So, thanks for watching this one. Thanks very much.